Okay, so I think I can start.
Yes, sir.
So, Osek, today we'll be discussing analysis part of this pavement portion, especially analysis of flexible pavement. So, we already did this analysis using the software CanPave, right? So,
Yes, sir.
how to do it manually, that we also should know, right? In case of like suppose the software is not available, then some charts are there. Have you printed those charts? Are those printed copies with you?
No, sir.
No. Okay, no problem. So I still request you to open those charts in your second device. Anyway, so if you remember, in our flexible pavement design, we needed to ensure one thing, that the strain, especially the horizontal tensile strain at this interface and the vertical compressive strength at the top of the subgrade, it should be, this generated strain should be lesser than the expected one, which is expected through traffic. Okay, and we call this permissible, right? So this generated should be lesser than the permissible one. Then we can say that our pavement will like yeah. So in that case, we can say that our pavement will last for the design life at least. Okay, so now we'll learn how to calculate those permissible strains because of wheel load at this interface, how this epsilon t is calculated at this interface, how epsilon p is calculated, or if the system is one layered, then how it will be different. If the system is two layered, how it will be three layered. I have skipped. So one layer and two layer, we will learn how to analyze. Okay, so before moving, let me ask you one thing. What is the difference between stress and pressure? Whatever comes to your mind, just tell. What can be the difference between stress and pressure?
So stress is actually the reluctance of the material, the opposite force given by the material when a force is applied to it per unit area, and pressure is the actual amount of force applied.
Okay, so you are saying that pressure is external and stress is internal.
Yes, sir.
Correct?
Yes, sir.
But still we say that this much of stress is applied on the material. Why?
Sir, because we assume that the material is elastic.
Okay, so you are saying that whatever externally we are applying, internally same amount of pressure or stress will be generated.
Yes, sir.
Okay, you are correct. Now, what is the limitation of pressure? Like, if I say, if you are explaining this to some layman person, then what can be the limitation of pressure because of which we have to, like, we need another term called stress? If you are saying pressure and stress will be always equal, then why to introduce another term? What
Sir, yes, sir. Sir, the pressure, the concept of pressure might go beyond the elastic limit when the behavior of an object to a pressure or something becomes very unpredictable. That is why we use the term stress to confine it within the elastic limit.
Okay, let me ask you in this way. If I suppose this is my object, okay, this is my object. If I apply some force, say F, and this area is A, so F by A will be what? Pressure
Pressure, yes, sir.
as well as stress.
Yes, sir.
Okay. Now, because of this force F, do you think this will be the only stress generated in this object, in this sigma, with the only kind of stress that will be generated in that object?
No, sir.
What kind of other stresses that can be generated? Suppose this is normal, you can say this is normal stress, because the load is acting normally or perpendicularly to the surface, right? So this is normal stress. What can be the other type of stress?
Sir, depending on the angle, there might be a shear stress as well.
Shear stress
And
as well. Okay, shear
but
stress. Okay, so everything can be converted to normal stress and shear stress based on their components, right? So
yes.
this shear stress, do you think we can come up with a terminology called shear pressure?
No, sir. I don't think so.
No. That's the limitation of pressure. In case of pressure, the force will have to work perpendicular to the surface. Okay. But in case of stress, we can define normal as well as shear based on how the force is acting on the surface. If the force acting is tangential to the surface like this, then this surface is say AY, then this is F, then F by AY, you can say this is our shear stress, right? But there is no term called shear pressure. In case of pressure, the force and your surface have to be perpendicular to each other. Understood? Now,
Yes, sir.
now let's go to this concept. What is stress at a point? This is stress at area, okay, right? These things, sigma n, this tau, this is force divided by area. So we are considering this area, this entire area. That means we are saying that any point on this area will be getting similar stress. Is it true? No, right?
No, sir.
Why? You see, these materials, they will start cracking generally from one random point. Okay, so from here it will start cracking. So that means what? The stress at this point exceeded the stresses at other points. If the stress is uniform throughout the surface, then why do you think the stress at a particular point is greater than the stress at other points? That's because stress at points will vary from each other. Cannot be same. You cannot generalize. Okay. So now coming to the concept of stress at a point, have you ever heard of a term called tensor?
Yes, sir.
So any idea what is it?
Sir, it sometimes describes the relationship between vector objects.
Okay. Anyway, that will be a whole different lecture. Quickly we will see how this stress at a point like is assumed, because this concept will be related to while solving the other numericals. So now if I say this is my object and this is my point, now if I want to say that want to define the stress at particular this point, then we will need a surface, right? Because ultimately here also some surface can be there, right? But this surface, suppose delta A, it will tend to 0 because this is at a point, so the surface will be 0. But the problem is this surface, the direction of this surface can be anything, right? It can be like this, it can be like this, it can be in any directions. Okay, if the direction is like this, it can be a shear stress. If the direction is like this, it can be, if the force is coming from this, it can be a normal stress. So direction can be anything. So we need to define the direction of not only the force but also the surface, the infinitesimally small surface at which the force is acting. Okay, so we can assume different, you know, surfaces. First, let's assume it to be like this. Then we can find out this surface and its directions. So what will be its how its direction is defined? The direction of a surface is defined. Any idea? Like this surface is on YZ plane, right? It is on YZ plane. So how this direction of a surface is defined? You must have learned these things in solid mechanics, right? So when we tell sigma xx, what does it mean? Or say sigma xy, what does it mean? What is the difference between this and this? Or say sigma yx, what is the difference between this and this? Prosec. Okay, so this the first terminology, whatever the letter is, it defines the direction of the surface. Now in this case, my surface, if I consider it to be on this Cartesian system, then if you see the surface is on YZ plane, right?
Yes, sir.
Then its perpendicular direction will be in the x direction. Okay, so that's why the area of the surface will be like termed as delta AX. Understood? If I take this
Yes.
surface, then its perpendicular direction will be in this direction. Then it will be called delta AZ. Understood? Devasis,
Yes, sir.
are you following? Devasis, are you there, Devasis? Okay, okay, fine. Now we have defined the surface. There can be different surfaces, but let's stick to the first surface, that is the surface on YZ plane, and we will define this as the area of the surface we will define this as delta AX because its normal is aligned in the direction of x axis. Okay, now this force, suppose delta P, it will also have some like misalignment. It will not be perfectly aligned with Z, X or Y direction. It will also have some misalignment, right? Just like in the engineering graphics class, the projection of line in axis, right? So just like that, if you assume that this particular force is acting in such a direction that it is making some angle more or less with all the three axes x, y and z, then we can again take components of this force in all the three directions, right? Its z component will be delta pz. That means if you take a torus and just put the torus in front of this delta p, then whatever height you will get, that's how I used to explain projection of line. Okay, so it will be delta pz. If we put the torus in this direction, it will show like sorry, if you in this direction, then you will get delta px, and again if you put the torus in this direction, you will get delta py. That means it's just the projection based on the angle. Okay, So now this delta P we have divided into three different parts, delta Px, Py and Pz, based on which surface? This surface, delta Ax. But this is not the only surface. If we like see, there can be different surfaces, right? So this surface, next we have to assume that okay, first for this surface only. Now if we say convert these forces in terms of stress, then how will it look like? First you will tell me what will be this delta Pz by delta Ax. You tell me this will be normal stress or shear stress?
Sir, shear stress.
Shear stress. Now should I write Zx or Xz or tau Zx for this particular?
Zx.
Why?
Sir, pressure in the x direction of
You are messing it up. I said the first letter always denotes the direction of the surface. Okay, it always denotes the direction of the surface. So in this case, what is the direction of this surface? Direction means you put a perpendicular to the surface and in which direction this is going to. In this case,
x direction.
X direction. So direction of a surface means always the normal, the direction of the normal put into the surface. Remember that. Okay. So in this case, my direction of the surface is X. So now you tell me. The second letter will denote the direction of the force. Now for this, it will be xz because the surface is in x direction and the force is in z direction, not zx. And why xz? Why tau xz, not sigma xz? Can you tell me?
So because the force is along the surface direction, it is not perpendicular.
Very good. Now, Devasis, can you tell me what will be delta Px divided by delta Ax? Similarly, what will be delta Px delta Ay? Sorry, Ay delta Ax.
So sigma xx.
Sigma xx, very good. And this one?
Tau xy.
Tau xy, very good. So the first letter will always define the direction of the surface. The second letter will always define the direction of the force. Now you have understood, right? So now this thing can be represented for this surface like this, same thing. Okay, so sigma xx is basically delta p. I am not putting this term, but since we are taking infinitesimal small area, so we need to put limit delta x tends to 0 because this is stress at a point. We cannot take this area. Okay, so that's why this term is coming. So now understood normal stress and shear stress?
Yes, sir.
Okay. Now for this surface, can you tell me what will be the stress components? Just think for 1 minute, both of you, and just let me know these values. What will be the direction of the area or the surface. Tell me here. What will be the direction of the area? It is on.
Sigma zx.
Think. No, let's go step by step. First, I am asking what will be the direction of the area. See, this is my surface in this case. So, the surface is on zx, right? Surface is on zx plane. So, its normal is in y direction. So, my area will be delta ay. Okay. And that will be again delta px, delta py, delta pz. We have to simply divide everything by delta ay. Now you have to just tell me which one is shear, which one is normal. So think and tell. Don't make mistake. Delta px by ay.
Sigma xy.
See, the force is, see, the surface is normal to y. So the only possible combination that can give you a normal stress is when the force is also thing like that. That means it has to be in the y direction. So the only force that is coming in the y direction is delta py. So this will be sigma yy, and this will be tau. This
Tau
part
yx.
yx and again
Tau yz.
yz. Okay, good. Understood?
Yes, sir.
Understood? For this case, can you write? No, I will not help this time. Just tell me.
Sir, the upper face, sir.
Yeah, the leftover face. Yeah, this is the upper face. That means area will be delta A Z.
So sigma zz.
Then you come serially, na? Delta Px, delta Py, delta Pz. So sigma zz will come at the third. What are the rest two? Tau
Zx.
Tau zx. Okay. Then
Tau zy.
Now I am actually very surprised with these things you don't know. We have never saw this matrix before. Sigma xx, sigma yy, sigma zz, tau fy, tau xz. And here tau yx, tau yz, tau zx, tau zy. You have not used this matrix before?
Sir, actually, sir, due to lockdown, sir, one of the semesters was very short. It was only 2 months. So that semester was when we got structural analysis 2 and 1. So we never got to use it.
This is not part of structural analysis. This is taught in solid mechanics. Okay. This is very basic. In GATE, you will face this type of course. There you cannot tell that due to lockdown we didn't learn. But online classes were going on, right? Yes, surprising. But this is basic. You should brush up these things if you don't know. Okay. Don't be shy. If you don't know, you can ask me, or you can anytime approach any faculty and clear out these things. It is your duty to learn. Okay. It's not always the teacher's duty to teach. It's the duty of the students also to learn. So from wherever you learn, it's up to you what you learn. I have a very good, channel link, YouTube channel, which clears these basic things like anything, with diagrams and all. Short videos, 8 minutes, 10 minutes like that. But your entire solid mechanics will be covered in 1 hour in such a way that you will never get confused. Okay, I will see and say. Okay. So, understood? So finally, this is our stress cube where we have all these different surfaces, different force directions, which are ultimately converted to a matrix of 3 by 3 size. Alright. Okay, now in order to do analysis of flexible pavement, we really don't need this much of information. This is again converted to some uh, you know system where the coordinates are not Cartesian, it's polar. Okay, so in this case, we will need only these two things: sigma z, sorry, three stresses, sigma r and sigma t. That means if you take a slice, if you can see, this is a slice like this, and this slice like this. So in this case, whatever it's acting radially to the center of the slice, that will be sigma r. Whichever is acting like tangentially to the uh, slice, it is sigma t, and which is coming from the top, that is sigma z. Okay. So if you remember, we use this term sigma epsilon t quite often, and one was the epsilon t. So epsilon t is basically will be coming from epsilon z. That's the top particle top strain. In tangential strain, it's acting like this. So if you consider, say, from this point, what is the tangential strain because of which it's coming like this? So it's this. So we will come to that. Okay? So in this analysis of flexible pavement, we will go step by step. In the first step, we will assume that our pavement structure is like one layer. One layer means only this infinitely large or long layer is there, where we called it half space. If you remember, the surface was called half space. That means there is no specific thickness for this layer, which is infinity. Okay, so here if you are putting a load, that means you go to your ground and you are putting some load, and the depth of the ground is infinity, right? So that's the one layer system. So here a half space, that means in this direction the thickness is infinite, so it's called half space. Infinitely large area and infinite depth with a top plane on which the loads are. So in this direction also it's infinite. Okay, so this theory was formulated way back, like almost 230 years ago. Right. So in this, I think you have heard this name, Bosenisk. Can anyone of you tell me where?
So yes, sir, Bolzan's equation there, it was there, sir.
Where?
Sir, there was in fluid dynamics.
No, soil mechanics, I think.
Soil mechanics, sir.
Bosenisk equation, Westergaard equations. Right? Anyway, so if you remember from the CanPEF classes, there we considered this as 0, right? This is 0, 0, this coordinate, and in this direction, whatever the direction we go, we measure this r from here, radial distance. But in this case, the center line is considered, this is considered 0, 0 in case of the manual method. And from this center line, radially how much you are going, the distance is called r, and depth is z. So get accustomed to this terminologies, r, z. Even in, I think, geotechnical class also, while doing this, using this charts, you are using these terms, z by a, R by A, right? So uh, basically there will be a wheel load of which you know the radius, contact radius A. You know how to find out contact radius. If this is load P, you know the pressure, tire pressure, small p. So P by small p is what? The area. And area is A square. Like this. So this is A. So basically this much is twice A. And this is A. Okay, I think you remember these things, right?
Yes, sir.
Okay. So same thing, twice A. This is Q there showing. Earlier we used the term small p. That is the tire pressure. We assume that tire pressure and contact pressure is equal. So this is the contact pressure basically, which is like the pressure exerted by the wheel load onto the surface. That is Q. Okay. And if we need to find out stress at any depth z, so this is half space, right? This is infinity. So at any depth, and radially at any distance, that means from the center, this is r, and from the depth, this is z. Now for the points which are like at any point, we need only two parameters to define. Okay? If this is 0, 0, then r, value of r will be from here and value of z will be from here. If we know r and z, we can directly say at where the point is situated, right? What will be the value of r here? This point, r will be how much? Come on, what will the value of r here? R means radial distance from the central line.
So it will be equal to Z.
Radial distance. I think you are not getting. This is my load. Okay. This is my central line from where r is measured. Okay. Symmetrically. Okay. And this is z. Now I am asking here at this point, what will be my value of r?
0.
Yeah, 0. And z will be something.
Yes.
And at this point, what will be my value of z?
0.
0. Okay. So basically from r and z, we can find out the location of the point, and this will be useful in finding out the stress and strains manually. Okay. So these are the charts. Alright. These are the charts. If you would have printed those charts, it would have been easier, but now you just only watch how to do, because we need to put scales and all. So now if you see, we need only three type of stresses here: sigma z, right? Sigma t and sigma r. These three stresses. Now if we see, these charts are already provided. How to find out sigma z, how to find out sigma r, how to find out sigma t. Okay, and if you see your charts, two terms are required. One is called z by a. Okay, z by a here, and numbers on curves indicates r by a. R by a. So that means this 4, 3, 2.5. This defines r by a. What was a? Again, what was a?
So contact area.
Contact radius. Okay. This is the area. This is twice a, right? So this is A. The contact radius, diameter is 2A, so radius is A. So everything depends on these three parameters only, R, Z, and A. Okay, with these three terms you can find out also Q, because if you see this term is there, so whatever you get, you will like find out sigma R by Q value, or here sigma Z by Q, or here sigma Z by sigma T by Q. Okay, so Osip has left. Similarly, tau RZ also can be found out. Okay, and this chart is used to find out the particle deflection. That means in this particular problem, at any point if I ask you to find out the particle deflection, you know, so here the shear stress is the tau RZ, tau ZR, both will be like equal. So, and if I ask you to find out deflection at this point, because of this it will deflect, so it will be, what is this deflection W, that can be also found out using this particular chart. The numbers on curves indicate R by A, so these are R by A, this particular things. Z by A is here, so F you can find out, and using F, Q, A, E you can find out what is W. Don't worry, we will solve too many numericals so that you will get a clear idea how to use these charts. Okay, now these are the stresses only, right? So we are not worried about stress. We need to know stress and strain because of those stress. So here we will use this formula. I think you already know this formula, right? Right? Epsilon 3, epsilon 2, epsilon 1, like that you learned.
Yes, sir.
Okay. So using this formula, if you can find out sigma Z, sigma R, and T, just by, and of course you should know this nu. What is nu? Cosec, say mu. If you are ignoring solid mechanics for get, then you are making a very, very huge mistake. Devices. Come on. Oh. Really? This much pathetic level of... This is Poisson's ratio, right? This Poisson's ratio. In these equations, if you need strain from stress, you need elastic modulus and Poisson's ratio. As simple as that. What is Poisson's ratio?
Yes, sir. Longitudinal stress plus 2.
Devices.
Sir, transversal stress to axial strain, sir.
Don't remember anything. Okay. So this is my bar. You are stretching it. Then this was originally R2. This will become R1 now. This was originally, so this was R1. This will become R2 now. Yeah, this has become R2 now. Originally this is L1. Now it has become L2. So basically delta R by R, which is R2 minus R1 by R, divided by delta L by L, L2 minus L by L. Okay. So this is L1 minus L2, I think. So this is Poisson's ratio. Okay. Anyway, now let's come back to our first numerical. See here, this all numericals are taken from this Wang book. I will share a soft copy with you, so you can find out other numericals as well. But in Wang book, the units are like British units. That means pounds per square inch psi. All right. So stress, unit of stress is in psi. Unit of uh, force is in pound lb, like that. Then unit of length is in inch. Okay. So since we are anyway finding strain, strain doesn't have any unit, so it doesn't matter which. If you convert these things to kilopascal, megapascal, and then you convert this thing into centimeter mm, ultimately you will get the same answer. Okay, so I suggest you don't convert this initially, you convert the final answer. Suppose you've been asked to find out stress, then the final answer you just convert some psi, you will get say 3 psi. So that 3 psi you convert by multiplying by 6.9. Okay, deflection you are getting 0.1 inch, so that you report is 0.254 centimeter, like that. Okay, so anyway, now let's understand what is this question all about. It says that a homogeneous half space, that means this entire layer it's talking about. Okay, you are sitting, that means the ground surface is subjected to two circular loads. That means two wheel loads are there, two tires are there, like this. Okay, each 10 inch in diameter. That means twice A is 10 inch. Okay, so how much will be A? A is 5 inch. Okay, spaced at 20 inch. That means this, okay, it's given. They are separated. Center to center spacing is 20 inch. Okay, on centers, the pressure on the circular area is 50 psi. Now they can use the term pressure because it's normal, right? So the pressure on the circular area is 50 psi. This, so that means this Q is given, Q or P. In earlier case we learned small p, tire pressure, contact pressure, Q. Here they are using the term Q. Okay, so it's 50 psi. So the half space has elastic modulus of 10,000 psi. That means the elastic modulus of the layer is given 10,000 psi. And Poisson's ratio mu is given as 0.5. Determine the vertical stress, strain, and deflection at a point A. Where is the point A? Which is located 10 inch below the center of one circle. 10 inch below one circle. Okay, here. It can be here also. Okay, it can be here also. Will it be different if I take it from here? If I take it here, will it be different? What do you think? What's your view on this?
So it should be different, sir.
Why? Why do you think so?
So because the z distance is you are taking it as different.
See, if I take this point, this strains, deflection, everything will come because of two forces, right? One because of this load, one because of this load. Because of this load, strain will be higher compared to this load, because this load is situated at a distance, not directly above the point, right? So R will be higher. If I consider this, for this will give maximum load, this will give like minimum, but ultimately it's symmetric, right?
Yes, sir.
Isn't it symmetric? So
Yes.
do you agree now that if I consider this point also, we will get the same values?
Yes, sir.
Okay. But if I make it 100 psi instead of 50, keeping this as 50 only, then will you agree with me?
No, sir. It will change, sir.
Now if I call this point B, so can you tell me where the stress or strain will be higher at point A or B?
Sir, at point B, sir.
Point B. Why?
Sir, because the distance from of point B from the greater load is smaller than
Yes,
the A.
yes. Understood. Very good. So Devasis, is it clear to you?
Yes, sir.
Okay, good. So now uh, can you start solving? Now how will you approach this problem? How will you approach? You know that there are different charts, right? So sigma r, sigma z, and sigma t, and tau rz. You need to find out all the values, okay, and deflection also, right? So, and ultimately we have to use this formula to find out the strains. Okay. So now can anyone tell me, since there are two loads, then how to take Q? How to take Q? How to approach this situation? Can anybody tell me? Because if you see here, unit Z by A and everywhere Z by A and R by A, right? So part to Z is a constant here. Z is constant, 10 is, right? What is A? 5. So Z by A is 2, right? What
Yes.
about R by A? What will be the R by A? Tell me. Hmm. See,
Sir, 1.
1. How?
Sir,
You
A
have just
is 5.
you just averaged it, right? No, not like that. We have to consider this as by considering these two loads separately. Okay. Then we will use the method of superposition. That means first we will simply neglect this load. We will just consider that only this load is there. Okay. And because of that, we will compute everything, sigma z, sigma r, sigma t, everything at this point. Then in the second scenario, we will neglect this load. We will consider that only the far load is there, and because of that, how much is sigma z, epsilon z, w, whatever, all those parameters. Okay. Then we will add those two values, sigma z because of this load plus sigma z because of this load, epsilon z because of this, epsilon z because of this, like that. Understood the concept? How to approach?
Yes, sir.
Okay. So now, uh, I highly suggest you open those charts in your mobile. Are you attending the class through laptop or mobile?
Sir, I'm attending to, sir. Where did you post those charts, sir? In classroom, sir.
In classroom. Yeah. You didn't get?
Sir, I did get, sir. Was it, sir, IRC 37 2018?
No, no, no. Uh, విన్నప్పుడు डिपार्टमेंट में हूँ, बोलो तो। हाँ हाँ, मेरा क्लास चल रहा है, 8:30 को ख़त्म होगा। हाँ ठीक है, आ जाना तो। हाँ, कुछ डाउट था क्या? रॉकफुक्स मेथड, अभी वो मत देखो, मैं तुम्हें कॉल करता हूँ क्लास के बाद, ठीक है? Okay,
Yes, sir. I found the sir.
you got? Alright.
Yes, sir.
Alright, anyway, so now we know how to approach this situation. So we'll make two columns like this. So due to load 1, due to load 2. Okay. Simply we are calling it, this is as 1, this is 2. Load 1, load 1, load 2. Now because of load 1, at this point, we are not worried about this. This anyway will be symmetric. Okay. They can ask you somewhere here, then this will be a different question. Okay. Now because of load 1, can you give me what will be the value of R by A and Z by A? Because of load 1 only, here, what will be the center line of the load? This A is exactly at the center line. So what will be R by A and Z by A?
Z by A would be 0.
0. Z by A we already found out. This is 10.
Yes, sir. 2.
10. So 10 by 5 it's 2. Right? So R by A is 0. Z by A is 2. Okay. Now because of these values, can you find what will be sigma Z? Sigma Z will be how much? See, R by A is given on the curves as numbers. Okay, so R by A 0 means the first curve. Okay, first curve, and Z by A given here, so it is 2. So where it is meeting, it's coming here like this. Okay, so if you go like this, it will be some 30. So basically, yes, this sigma Z by Q into 100 will be say 30. Right? What is Q? What is Q? Q is given 50 psi, right?
Yes.
So what will be sigma Z due to this one? Are you writing also with me?
Yes, sir.
Tell me. It's not 30 actually, it's 28. If you do it exactly, it will come as 28. So sigma Z will be how much?
So 14.
14 psi. Okay. What will be sigma Rn, sigma T, and tau Rz, W? What about these terms? Can you just tell quickly? What will be sigma R? See, R by A 0 and Z by A 2. So it will go and meet somewhere here. So it is almost
6.
6. So what will be sigma R?
So 3.
So 3, sir.
3. 3 psi. Are you sure?
Yes, sir.
Wait. Why? Sigma Z by Q, it will be 30. then this 50 or like here. It's correct only, right? 3
Yes.
0 minus 2. No, wait, it's not 0. This one, no? Coming here. This one is 0. It will be somewhere here. It is 2 basically. This value is 2. Sigma R by Q into 100 is 2. What will be sigma R?
1.
1. Okay. Now tell me what will be sigma T? 0
0.9.
into here. How? 0.9? 0, no? R by is coming here, meeting here. This is 2, it's going here. It will go 2. Okay. So, I'm saying it's not
So
1,
1.
it's a point. Okay. So this is 3, now it was 1, right? This is 1, this is also 1. What will be tau RZ?
Sir, I can't find a 0 line here.
Yeah. It's not given, 0 is not there. So, 1 second. Checking. I think that's not required also in the formula, right? It's not required. Leave it. So, what is W? It's the deflection. This is like little bit tricky. You have to find out F first. F will be 0, 2, somewhere here. That will be 1.68 maybe. So, need to multiply 70. A is 10, right? A is 10 or 5? 5. A is 5. Then E is how much? How much is E? 10,000.
So value of Q was 50, sir. Why?
50 or 70? Okay, 50.
50, sir.
50. Then F you have got 0.68. No, something inch. How much you are getting?
0.017.
0.017. So wrote everything. 0.017 inch. Now due to load 2, what will be R by A? Z by A? Just tell me these two values. What will be R by A and Z by A? Due to load 2 at the same point A. What will be R by A?
Sir, 4.
Yeah, R is 20. It's radial distance, right? So load group is this, your center line will be this. So from here it's 20 inch. A is 5. So R by A will be
4.
20 by 5, 4. What will be Z by A?
2.
2.
Yeah, it's same, right? Your vertical height is not changing, it will be 2. What will be sigma Z? Sigma R, sigma T, and W. Quickly tell. I will write both your values. You understood, right? How to do?
Yes.
Hmm.
So sigma Z is 0.4.
Devices.
Yes, sir. 0.4 psi.
Is sigma R.
1.25 psi.
See, you have to.
Yes, sir.
No, I don't think so. Is it?
Yes, sir. 1.25.
Okay. 1.25 psi. Then sigma T.
So there is no line for a 4.
Okay, so it will be 0. Can I take 0?
Yes, sir.
Yeah, so it's 0.24 like that, so 2.5. So ultimately it is becoming like this, right? It is becoming 0. If you see how the shape is changing, coming like this, right? Ultimately it will become a straight line. Maybe 0. Okay. Now simply 8. Yes. Total. Okay. Total due to load 1 and 2. You have to simply add this. It will be 14.4. Sigma R will be 2.25. Sigma T will be 1. Okay. Now can you find out what will be?
Sir, we did not find out W.
Okay. W. Tell how much?
Sir, 0.05.
Devices are you getting also the same?
Yes, sir.
0.05. Okay. So W will be 0.022. Yes. Okay. Now we need. Do you need
Sir, no, sir, there was a mistake, sir. It was actually 0.005.
0.005?
Yes.
Okay, but my summation is still correct. I made a mistake there. Okay. Now, how to find out the strings? Use this formula. We don't need all the strings, right? So let's find epsilon z and epsilon t, and tell me what is epsilon z. and epsilon t. E is 10,000. This is 10,000. Mu is 0.5. And you know sigma r, sigma t, sigma z. Come on.
Sir, 0.00127775.
Tell in terms of 10 to the power minus 4. 0.
Sir,
Okay. 001
277.
27. Okay, 28. Epsilon t, how much?
Sir, minus 7.32 into 10 to the power minus 4.
It can be minus 7
7.325 into 10 to the power minus 4.
minus 4. Okay. So you are selling, this is 732.5 microstream. And this is 1280 microstream. Okay. I don't know. I will check. Okay, so I'll give you the answer. So according to the book, answers are sigma z is 14.38 psi. Epsilon z is 0.00129 and W is 0.022. It's, I think you could get similar values, right?
Yes, sir.
Yes, very good. Okay, done.
Yes.
Now it will not be the case in case of a pavement. See, these things, this can be used in geotechnical also, because of a foundation, two foundations. So what will be the load at this point, at that point? So these concepts are universal. Okay. Now, in case of pavement, it will not it will not be a one layer, right? There will be different layers. So we need to learn how to do if there are more than one layers. Okay, more than one layer means the properties of the layers will be different, but there are some assumptions which you already know from soil mechanics classes, that layers are considered homogeneous. That means the material is same throughout the layer. Isotropic, that means properties at each point will be same. Linearly elastic, okay, that means stress and strain are linearly related. And that's why you are using those equations with elastic modulus E, Poisson's ratio nu. So the material is weightless, infinite in areal extent, like this. This layer has a finite thickness, so H, except the lowest layer, it's infinite in thickness. So this layer is half space. Okay. A uniform pressure Q is applied on the surface like this over a circular area of radius A. The radius is, contact radius is A. Okay. Now in two layer system, we can find the stresses at different layers as well as at the interface of layer 1, these two layers. That means this sigma c we can find out, also sigma z at the layer 2 and sigma z at layer 1. So this can be found out using the equations given by Burmester in 1943. So this type of scenario will be there if you are constructing a full depth construction in which a thick layer of HMA is placed directly on the subgrade. That means the subgrade is there, soil, and above that there is no base layer, no sub-base layer. Directly you are putting a HMA. HMA means hotness as well. This bituminous layer you are directly putting there. So, or in that type of situation, you can use this two-layer system. Okay. So here you can find out sigma z using this chart and sigma c at the interface using this chart. So this modulus ratio E1 by E2, basically E1 is the elastic modulus of the top layer, E2 is the elastic modulus of the bottom layer. Okay. And A by H1, A is always the contact radius, so H1 is this first layer thickness. Second layer thickness is infinite, right? So we only need to know the first layer thickness. So if you know this information, A, H1, okay, E1 by E2, you can find out at the interface what is the stress. That we need to know because of writing, you know, it is calculated at the top of the subgrade. We need to know what is sigma c. Okay, so let's do a numerical. Alright, so let's understand the question and let's write down the information given. It is said that a circular load having radius 6 inches. Directly you can write down A is 6 inches. Okay, uniform pressure 80 psi, Q is T psi, is applied on a two-layer system. So this is two-layer system. If you can see the diagram as shown in the figure, the subgrade has elastic modulus 5000 psi. That means this E2 bottom layer elastic modulus 5000 and can support a maximum vertical stress of 8 psi. That means at this interface, that sigma c that is calculated at the interface, maximum it can support 8 psi. Otherwise it will fail at this point. Okay, so it is 8 psi. That means we can say it is the bearing stress of the soil layer at the surface. If the HMA has elastic modulus of 500,000 psi, that means this layer has a 500,000 psi elastic modulus, what is the required thickness of a full depth pavement? So H1 is unknown here. It's a tricky question. They are saying that, so basically you need to find out solution of this type of problems where you need to find out what should be the depth of the layer you need to provide. Provided the load, the stress at the bottom of the layer, that means the soil can take a maximum of 8 psi stress only. If it is more than 8 psi, it will fail, the soil will fail. So we will restrict, we know that sigma c maximum can be 8. Are you understanding the problem here? Okay. There is a second part also. If a thin surface treatment is applied on a granular base with elastic modulus 25,000 psi, what is the thickness of the viscous required? So now it is saying that instead of this HMA bituminous layer, now if you are providing a granular base layer, so granular base layer will be having very less, elastic modulus. If you remember from the numerical solved for the design, lowest elastic modulus is for subgrade then granular layers, then bituminous mix, right? So granular layer is only 25,000 psi. So in that case, what will be H1? At least you can tell me which H1 will be higher in quiz part A or part B, where H1 will be higher. Tell me.
Sir, where are the points A and B, sir? I can't.
No point A and B. Same question. Same question. Instead of providing this layer with elastic modulus 500,000, this time you have to provide a granular layer with 25,000 psi. So in that case, what should be the thickness of the granular layer? Same, there is only one layer, either bituminous mix or granular. So you need to provide higher thickness for the bituminous mix or the granular. What do you think? To generate same 8 psi here.
Sir, higher thickness for the granular.
Yes, of course, because granular layer, the elastic modulus is very less. So whatever the force is coming, it will not be able to distribute to a greater area, right? So it will distribute like this, and because of that, the force stress generated here will be higher. So we need to provide more, so that ultimately when it comes like this, the load becomes, this gets distributed. Okay. So here H1 is unknown. So out of this, which one do you think should use? You should use this one or this one? See, we are not finding sigma z. Sigma z was here, either this at this layer or at this layer. We are finding the stress at the interface, right? This is given 8 psi, right? This H1 is to be found out. So can you use this one? No. Can you use this one?
Yes.
Yes. So sigma c known, Q is known, E1 is known, E2 is known, A is known. We need to find out only H1. So let's have some brainstorming session. Have you written down all the formula, or I mean all the values?
Yes, sir.
So can you give me the thickness H1? Because not everything should be spoon fed, right? For part A and part B. The only thing is, in part A, your E1 will be how much?
500,000.
500,000, and in part B, E1 will be 25,000, right? So you just tell me this. Devasis, are you getting?
Yes, sir, I'm getting.
Sir, in E1 is equal to 500,000, it H1 came out as 18.75.
Devasis?
Sir, I think I did some mistake. Mine is 5.45.
Okay. I don't know which one made mistake. But 18.75. Let me check. Find out B, part B. I think Devasis was correct. It's 5.2. Can you check again? U1 by E2 will be how much for part A?
So 10.
10 or 100?
Okay, so
100,
my
sir.
bad, so it was 100.
Yeah, it is 100. So this line. Sigma C by Q will be how much? It's 8 by 80, right? It's 0.1. It will go here, will cut here, will come like this. So A by H1 is how much? A by H1 0.8, 0.9, 1, 1.1, I think almost 1.1, right? So H1 is 6 divided by 1.1. How much?
So 5.45.
0.45. What about part B, versus
So I found it as 15 inches.
15 inches?
Yes, sir. 15 inches.
15 inches. Very good. Yeah, it's 15 only. So you see, in order to produce, so every numerical you try to visualize. So there is a ground surface. Above that, you need to uh, provide some layer. Okay. So if we provide the layer of bituminous mix, then we need to provide only 5.45 inch thickness to produce the same stress at the surface of the earlier layer. But if you provide granular layer, you need to provide 18 inch, this much. Now it becomes now which one you will provide? You tell me, basic question.
Bituminous.
Why?
Sir, since the height is less, so the material required is also very less.
But bitumen is very costly.
So there must be some kind of combination which is optimal. Neither one is, I think.
See, here as an engineer, you need to figure out the other options also. Like you need to do cost analysis. 5.45 inches, although the thickness is less, but the cost can be in crores. Suppose granular materials are already available nearby, so you can use freely. Then this 18 inches can cost you only 1000 rupees, let's say. So this type of situations you have to judge. It's not always about the thickness. Sometimes it is about the cost also, availability of the materials. Suppose you have a bitumen plant of your own, then you will provide 5.2 inches, 5.45 of bituminous layer, because granular materials queries are banned in your state, in your district, so you cannot get this much of aggregates. So there can be many. Okay. Now finding vertical deflection. So in this two-layer theory, we learned how to find out the stress. Suppose you are asked to find out the deflection. What is the deflection? That means if it bends like this, what will be the deflection here? Okay. So in that case, we have to use this chart where U1 by E2 and the number on the curves, and F2 is using found out using this formula. Actually this formula, I think this is 1.18. okay, 1.18, not 1.5. okay, so we write down this formula. W0 equal to 1.18 QA by E2 F2. So that if you can find out F2 using H1 by A, directly you can find out the deflection. Wrote down. Now quickly do this problem. A total load of, in this question I will not help much. I want you to think, okay, because here the trick is involved in the first line itself. Okay, directly they have not given Q or anything, so you find out everything. Tell me on the surface, is a plate 12 inch diameter, so A is given, A is 6. The layer 1 is 8 inch, this H1, and layer 2, this one is given. U1 you need to find out. Okay, if the deflection of the plate, so this deflection is given. Okay? Deflection is given, this deflection here or here, it's how much? 0.1 inch. Okay, then find out what is E1. This is the curve. This is pound, okay? Pound.
Sir, are the curves given in the vertical deflection for E1 by E2?
Yeah, E1 by E2. These are E1 by E2. So basically you need to find out which curve, because you don't know E1 by E2. Okay, so first you need to find out W naught is given.
Yes, sir. I found out F2 as 0.054.
0.054. So if somewhere here, then it will go like this. H1 by A is how much?
1.33, sir.
1.33. So 1.331. So it will be somewhere here. So which curve?
Sir, between sir 3500, sir.
Mm-hmm.
Sir, 3500, sir.
0.05. Are you sure? They are getting F2 as 0.511. And check your. This is 1.18. Okay. Use this formula, not this.
Sir, Q was found out as sir 1666 psi. Is it right, sir?
1666. No. Q is 176.8. Nevertheless, you are quite. How did you find that Q? Simple, na? P by A is Q. So it's 20,000 divided by area is pi r square, pi a square. A is almost 6.
Yes, sir. F2 is coming out as 0.5112.
Okay, so 0.511. So somewhere here.
And so
There was-
H1 by is 1.
If you go like this, so which curve? Almost this curve. You can interpolate also, but say this curve 5.
So 5.
So E1 by E2. Devasis, are you getting? Are you following?
Yes, sir.
So how much F2 you are getting? Devasis, if you are not getting,
So
tell me.
earlier I was done it wrongly, but now after that,
Okay,
now it is 0.51.
okay. So E1 by E2 is 5. So what will be E1?
Sir, 30,000 psi.
30?
32,000 psi, sir.
Yes. Now, you think and give me one scenario where this type of numerical can be useful. Just read the question and give me a situation like real life example where this kind of solving this numerical will be beneficial.
Sir, when we can only build the road up to a height, up to a given height, and we need to select the material accordingly.
Okay. Now I give you one more relatable example. Suppose there is a pavement layer on ground, directly over ground. You want to know what is the elastic modulus of the pavement layer. You know that if you want to find out this elastic modulus or modulus of resilience, you need to take sample, do some laboratory testing, use procedure. So instead, what you have decided, you have taken a rigid plate, kept it, and over that you have put some load. Okay, 2000 pound or 89 kilonewton. You have put it, and with dial gauge you have measured how much it has deflected. You found out that 0.1 inch it has deflected like this. Now you know the elastic modulus of the soil by CBR test. You have performed CBR test. From CBR test, you know the relation, right? If CBR is less than 5, then elastic modulus is directly 10 times of CBR. If it is greater than 5, then 17.6, blah blah blah. Okay, so you know this. So can we find out elastic modulus of this layer? We have indeed found out, right? This is coming out as 32,000 psi. Okay, so understood how things can be related to real life scenario. So the
Yes, sir.
concept of plate load test is also similar to that. I think you have heard of plate load test.
Yes, sir. In geotechnical engineering.
Hmm. So the concept is more or less similar. That's how it's done. And I'm again surprised that you have not used this equation. You have not used this equation
No, sir.
while preparing for GATE. I think you should come across this equation where 1.18 for rigid plate, for flexible plate it will be different, like that. In foundation engineering, generally these things are taught. Okay, so that's it. Now, finding particle deflection. So here we have found out the deflection here at the surface. Okay, what will be the deflection here? And also remember, this is rigid plate. Okay, this is rigid plate. That means uh, there will not be any much of deflection in the plate itself. But in case of wheels, they are made of tires, right? Pneumatic tires. So they are not rigid, they are flexible in nature. So in this kind of scenario, how to find out deflection at an interface of layer 1 and layer 2, that we will find out here. Okay, so for this, write down this formula: W equal to QA by E2 into F. Right?
Yes, sir.
Okay, so here lots of curves are there, and you have to observe this value. E1, this entire car, like this graph, is for E1 by E2 equal to 1. That means same material. Both the materials are may not be same, but elastic modulus is same. Okay, so this is for 2.5, for 5, for 10, 25, 50, 100, like that. Now we'll solve this numerical. Are you ready?
Yes, sir.
Okay. So now it says that a set of dual tires, this one, each having contact radius 4.52 inch. This radius is 4.52. This is A. Okay, and contact pressure, which is Q. Q is 70 psi for both. The center to center spacing of the dual is 13.5 inch. Layer 1 has a thickness of 6 inch and elastic modulus 10,000 psi. Okay, layer 2 has elastic modulus of, so this is 100,000, this is 10,000 psi. It's 10,000. So it says determine the vertical deflection at point A, which is at the interface in at the center of one loaded area. Can you find out which chart to use? What will be E1 by E2? Come on, what is E1 by E2?
10.
10.
10, sir.
10. So which chart you will be using? This one, right? Now one question. Suppose E1 by E2 is 15. Then what will you do? There is no chart for 15. Tell. Come on, think. Think and tell. How do you get F? Or E1 by E2 equal to 15. Can you tell?
No, sir.
you will find out f corresponding to u1 by a to 10, then again f corresponding to 25. Then you will interpolate both the values of f. Okay.
Yes, sir.
So now in this case, you can use this to tell me what is f. First, tell me f. What is the value of f?
Sir, can you go to the previous diagram, sir? I did not write some data.
Okay.
Okay, sir. Yes, done.
So tell. So here again you have to use the method of superposition. That means consider only this load first, find out f, then consider only this load and find f. Then sum up both the values of f. You tell me how much, and how much. Can you? What will be R by A for load 1? This is load 2. What do you need? R by A you need, right?
Yes, sir.
Numbers on curves indicate R by A. H1 by A is constant only. 6 by
Yes.
6 by A is 4.52. So it will be something. 6 by 4.52 is 1.33. So H1 by A is 1.33. E1 by E2, then it's 1.33 somewhere here. 1.5, 1.33 somewhere. We'll go like this. What is R by A for the first load?
So 0.
0. So where is the 0 curve? Like this, it's coming. It's going up. So I think 0.58 or something. F. Right?
Yes.
F1, let's say, or 0. In the second case, what will be R by A for the second load? It's 13.5.
Sir, 3.
Yeah, 13.5 divided by 4.52. It's 2.99 it's coming. Are you also getting 2.99?
Yes, sir. Yes. 2.9.
You can consider 3. Sorry, this is not F. This is R by A. So 3. 1, 2, 2.5. 3 is this, I think. It's like this. It's going. I think it's 0.27 or something. F2.
Sir, deflection is W, right, sir?
Yeah, deflection is W.
Sir, W was given as question mark. How did we find out W, sir?
Yeah, that's what you need to find out. W. For that unit, you wrote this deflection. W is this. For that unit F, right? So we are calculating F.
Yes.
This formula. I think here it's wrong. It's not Q suffix A. It's QA. Okay, Q into A.
Yes.
So F is some due to load 1, it's 0.5. In the book it's 0.56, and due to load 2 it's 0.28. Okay, it's 0.84. Are you getting this value of f? Both of you?
Yes, sir. Yes, sir.
Okay. So
Sir, how did you find out f from sir r by a? So using this chart, right, sir?
yes, yes.
Okay, sir.
Here, see, for this e1 by e2 equal to 10 h1 by a is 1.33. So I go like this. So for r by a equal to 0 for load 1, I found out f is 0.58. For the second load, r by a is how much? 3.
Three, sir.
Uh, so for this, I found out it's coming around 0.27.
Sir, understood, sir.
Understood? Okay.
Yes.
So how much? What is the deflection? Can you tell me?
0.027 inch.
0.027 inch. Okay, good. Okay, so that's a deflection. But we, for bituminous mix, we also need the tensile strain, right? Epsilon T. So for tensile strain, we use this chart. Okay, so this is the formula, and let's quickly do one numerical and find out what is the tensile strain using this chart. So it says a full depth asphalt pavement. This is full depth means only asphalt pavement is there. Take subject 18. Okay, H1 is 8. Subjected to a single wheel load 9,000 pound. Having contact pressure 67.7 is Q. If the elastic modulus of the asphalt layer is okay, this is given. This one is E1, and this is E2. Determine the critical tensile strain in the asphalt layer. What is the tensile strain here? Come on, I'll not help. First find, you see in the curve, what do you need? You need to find out E, right? For that you need Q. Q is given, E1 is given, FE is not known. So FE you can find out from this chart, and in this chart, what do you need? E1 by E2 are these values. These are E1 by E2s. Okay, and these values are H1 by A. So E1 by E2 already know 10, I think. H1 by A, how much? H1 is 8, A you don't know. First you tell me, let's go step by step. What is the value of A? Let's not make mistake the first step only. What is the value of A you are getting? Hmm? Come on.
7.52.
Huh? Why are you making mistake again and again? Pi A square is the area. Okay. And load divided by area is Q. Q is given, load is given. Find out A. What is A?
So 6.5.
Devices. Devices, are you getting 6.5? Kosik, you continue.
6. Yes.
Yeah.
6.5 inch.
So what is H1 by A?
1.23, sir.
So 1.23.
What is E1 by E2? 10.
Yes.
So what is FE? 1.5, 1.25 will be this one. So it is this one. Then 10 is coming like this. So here again you have to go this way. So this is 0.5, this is 1. So this will be around 0.75, right? So in the book it's given 0.72. Okay. So if it is 0.72, can you find out what is E? That is E. E is epsilon T. How much?
7.67 into 10 to the power minus 4.
3.25 into 10 to the power minus 3.
Minus 3 or minus 4? It is E1. E1 is 150,000, not 15,000.
Oh, yes, sir. Sorry, sir.
Kosik, are you getting?
Yes.
Okay. So, so we are saying that this value will be this much here. Okay. So can we confirm this with CanPEF? Shall I try with CanPEF? Whether
Yes, sir.
the manual method is. So I am presenting another screen now. Please switch your screen. Okay. Can you see my second screen?
Yes, sir.
Okay. Now I think you have already forgot how to use CanPEF, or you remember?
Sir, some things I remember.
Okay. Okay. File, new, then here let's go one by one. This is linear, so it will be 1. Damage analysis we don't know, it will be 0 itself. So you don't have to do, I am doing. Okay. So number of periods per year, it will be 1 only. Number of load groups. So number of load groups will be how much?
2, sir.
Why 2 in this question?
So in this question 1, sir.
In this question 1. Number of load groups. Check. That will be 1 only. Number of layers.
So 2 layers.
Yeah, 2 layers. Number of Z coordinates for analysis. How many variation in Z?
So 1 will.
Only, sorry. 1. Maximum cycles, it was 80, right? Type of response, unit what? Strain, right? So if you unit displacement plus stresses plus strain, so you get like 9. All the interfaces bonded, yes. Bottom pencil. And system of units, what shall I write? 0 or 1?
So imperial units, sir.
English. So 0.
Yes, sir.
Okay. So in z coordinate, sorry, it's done. Z coordinate, what is the value of z?
So 8 inches.
8. 8. Then layer, first layer, what is the thickness? 8. Poisson ratio not given,
Yes.
so we'll write 0.5 only. 0.5 in both the cases. Okay. Then modulus, what is the first layer? Modulus?
So 150,000.
150, then 3 zeros, then 15,000.
Yes, sir.
Okay. Then load. So here you see load. You read this statements. Okay. Load, type of loading, assign 0 for single axle with single tire. So what shall I write here? 0 only, right? What was the second? CR. CR is contact radius. So how much contact radius shall I write?
So the A into 2.
Contact radius.
13, sir.
Huh?
Sir, radius, sir, 6.5.
6.5. CP is contact pressure. How much?
Sir, 67.7 PS.
67.7. This YW and XW, center to center spacing, assign 0 if there is only one wheel. Okay, XW, only one axle, so both will be 0. NR and NPT, it's the number of points, right? So here I'll write 1. I enter, it comes to the radial distance. So what will be my value here? Remember, here in CANPEF, our 0 starts at from the edge of the tire. So what will be RC here?
6.5.
No, 6.5 divided by 2.
Yes.
6.5 divided by 2 will be 3.25. Right?
Yes.
Okay. Done. Okay. Save as ZIST underscore 005. It's saved. Exit. Run can layer. Done. Graph. Okay, it's fine. Let me go there. Let's compare. ZIST 005. So tangential stress, how much it's showing?
3.17. We got 3.25.
3.25. So more or less similar.
Yes.
So this is not something like giving very absurd values, right? So in case you don't have software, you can adopt this. You see this charts were generated in 1900s and all. The computer generated use FEM software and they give accurate results. But still you see how close we are, right? So yeah, that's it. That's it. Analysis of flexible pavement. Devasis, you didn't attend this design part, right?
Yes, sir, I was absent in the previous class.
Yeah. So CANPEF, the software you learn, this is useful.
Yes, sir. So I've asked my friend Kosik to teach me how to do it.
Okay, you can watch the videos also. Videos are uploaded, so it's
Okay,
shared
sir.
in Google Classroom.
Okay,
Okay,
sir.
so um, it's 8 o'clock. Let's stop. And tomorrow, I think the day after tomorrow you have exam. So
Yes,
let's
sir.
not
Okay, midterm.
let's not take any class tomorrow. So when your midsem is finishing.
Yes, sir. We have 3 days of midterm, sir. Up to Wednesday.
Okay. Okay. So next Saturday we can have our result class, right?
Yes, sir. Yes, sir.
Okay. Okay. So we'll start with rigid pavement. Design or analysis, I will think and let you know. But for rigid pavement, the problem is I don't have slides, so I will take permission from my supervisor whether I can use his slides. But it is not PPT; it is in PDF mode. So in that case, I will not be able to share the slides with you. So if you need to refer anything, you just watch the videos. Okay, take screenshots or whatever. I will share the code also and share this book also. One. So is it interesting? Are you learning something new, different, interesting?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So it's interesting, and since you are attending these classes very sincerely, so you can think of pursuing, career in transportation engineering, because this is very advanced level you are learning. So I don't know, in your next semester this course will be floated, I heard, but I'm not sure whether up to this level it will be taught or not. But you are learning what people generally learn during their MTech course. So take advantage. You can take advantage of that and get a very good gate score. Okay, then uh, if you want to join IIT Madras for MS, Master of Science or PhD program, direct PhD, um, you can like let me know. I will pass forward the information to my supervisor. He wants to take good students, and uh, you seem to be good students to me. Okay, both of you. So if you are really interested, then let me know. But the thing is, you need to have a good gate score. Okay, not high enough that you will get. You are not applying for MTech. Okay, so for MS and PhD, decent enough good gate score is enough. You can directly get. Okay, you have to just give an interview. So yeah, that's it.
Okay.
Prepare well for GATE.
Okay, sir.
All
Thank
the
you, sir.
best. Thank you.
Thank you.
Thank you, sir.
Bye.